Alright, this week's video is going to be a little bit different, and that's because this week it's the National Astronomy meeting hosted by the University of Bath for the Royal Astronomical Society. Essentially, it's the week where all UK astronomers and friends get together and share all the research they've been working on and any new findings. I myself am going to be presenting at the end of this week on Friday as well, all about my latest research on how supermassive black holes grow, and I figured I'd bring you guys along for essentially what is going to be like a week in my life vlog, and also at the end of the video explain to you guys what I've been up to the past year and what my latest research findings are. I am not in Bath though, I am still in my house because this meeting is also virtual. COVID cases are really high in the UK at the minute despite our high vaccination rates because of the Delta variant, and so it would have been very irresponsible for 800 astronomers to descend on Bath in a single conference centre. So once again I'm just going to be at my desk in the spare room / office / filming studio, or maybe even at the dining room table as well. But this week there's a twist because the south of England also has a weather warning for extreme heat. It's not even 9 a.m. here and I'm absolutely boiling. It's going to be over 30 degrees Celsius for the next 4 days here, which I know probably won't sound that warm to a lot of you around the world, but please remember our houses are made from brick and designed to retain heat, and we don't have any air conditioning. So essentially the house, it's hotter inside than it is outside most days when it gets like this. So staying inside to attend a virtual conference is going to be interesting, to say the least. So I think this week is going to be exhausting, but fun as well. And I'm really looking forward to, just catching up with colleagues as well that I haven't spoken to in over 2 years since the last NAM that we had, because last year it was cancelled, 2020. Heads up, this video is sponsored by Brilliant, so stick around to hear more about them if you want to know how you can learn maybe more topics in science and maths. Perhaps you have a dream of becoming a scientist one day as well. But let's kick off day one of NAM. I'm about to go basically sit down at the dining room table and check in with some of the sessions this morning. But also this morning, we're kicking off with the very first plenary. This is one of the talks that everybody goes to, and it's by the one, the only, Professor Dame Jocelyn Bell Burnell. Her talk is all about Caroline Herschel and her connection to the city of Bath. You can actually go to the house in Bath where Caroline and William Herschel lived, where they discovered the planet Uranus. I went there a few weeks ago and it was such an incredible insight to history and working in that time. It's only the end of day one and I'm already exhausted. It's gonna be a long week. But a fun week, but a long week. So I'm now at one of the plenary sessions on fast radio bursts, or why I finally left the galaxy, which is being given by Victoria Caspi, who is a professor at McGill Space Institute in Canada. She used to work on just magnetars in our own galaxy, and she's sort of been wooed away by the mystery of fast radio bursts, essentially. So this talk is going to be great. There are 416 people currently in attendance virtually, because this is one of the talks that everybody attends at the conference. It's not like the parallel sessions from before where you had to pick which of the topics you actually wanted to go to. These are scheduled so everybody can go, and so I'm really loving this talk so far. I'm really interested to hear from Victoria about how she went from magnetars to fast radio bursts.
Later.
This is multitasking at its finest. This is the NAM session on cosmic star formation that I'm just taking notes on down here. See a new talk on the evolution of the quiescent galaxy mass size relation from redshift 0.7 to redshift 1.2. And then there's Jeff Bezos just blasting off from space. I've got 2 live streams going. It is day 3 of NAM, and I feel like we've gotten 3 days in and I haven't really vlogged that much yet, but I think that's going to change today because this is where things start to really ramp up for me. All of the galaxies specific sessions really kick off today, tomorrow and Friday as well. So the sessions that I'm involved with and have organized and have helped organize. So later on today at about 4, I'm actually chairing a session, which I'm really excited for. But before that, I've actually got to upload my Night Sky News video that comes out tomorrow, which I was up really late last night finishing the edit for because I can't edit during the day because NAM is on. So that's been fun, and that's what my day looks like, and I'm really looking forward to it. So I guess I'll see you, I don't know when.
8 hours later.
All right, so I just finished chairing my session at NAM, and oh my gosh, it was so chaotic. I'll tell you about that in a minute. It was all about low surface brightness galaxies. Low surface brightness features are essentially the really faint features around galaxies that you can only see if you expose your image for ages. And I'm talking ages, like a whole night for one galaxy, that kind of thing, with a professional telescope. It's a really long time, right? So these features can actually tell you a lot about the history of a galaxy. They can tell you if a galaxy has had maybe a merger in the past that you can no longer see, you know, like two individual galaxies merging anymore, but you can maybe see the sort of like echo of that merger in all of these faint features around it. Or perhaps you can see that the galaxy's had an interaction in its history because there's been some stream that's pulled off the galaxy thanks to gravity as well. So these things can tell you a lot about the galaxy. So the session was really interesting because yes, there was people who were looking at these kind of things observationally, but also in simulations as well, which I haven't seen before, right? People trying to simulate this and also trying to simulate how you would observe it as well. And then also just, you know, simulating dwarf galaxies, like tiny galaxies as well, that are also really faint galaxies, so you need to observe for a really long time. So it was a really cool session and I really enjoyed it, and I had fun chairing, you know, sort of like fielding the questions from everybody and being like, 1 minute left. Like it was a little bit of like a I'm in the power seat or whatever, so that was really good fun. But honestly, like this morning I checked the schedule and I was like, when does the session start this afternoon? Right? Looked it down, it started at 4. So later on today at about 4, I'm actually at about 4. So I was like, okay, I'll rock up at about 3:30 because me and the other session organizers, we want to, you know, just discuss how do we want to chair it? How do we want to, you know, field questions from everybody who's watching? How do we want to tell people that they've got 1 minute left? All that kind of stuff, because it's virtual, it's a bit different than we're used to in normal conferences. And then we can just have a bit of a chat, have a catch up, you know, all that kind of stuff. And unbeknownst to me at like 3:25, I was in my own little world. I can't remember what I was doing. I think I was prepping like for my own NAM talk on Friday at the time. And I was just ignoring emails, and I was just getting a lot of emails from my collaborators like, are you coming to this session? Because you know it starts at 3:30, right? And I was like, oh shit. So I turned up at 3:30 as it was starting, and the session organizer just handed over to me like, and Becky's going to be chairing. And I was like, okay, our first speaker is just so chaotic. And of course, I picked today to be like the day that I decided I don't need the fan today. You know, I'm going to try and do it without the fan. Why? Why did I decide that? It's still 30 degrees and I'm still in, you know, what I've now dubbed the sweaty spare room sweat box, because it's just so hot in here. And I think that just added to the chaotic energy. But, you know, I feel like people just expect that from me now. So just anyway, I think it is time for a drink outside in the garden in the shade. Also, just came downstairs, you know, to just make myself a drink after that little chaotic chairing thing. Checked my YouTube analytics and saw it go from 299,999 to 300,000. Like, what on earth? 300,000 of you. So this drink that I'm, you know, abandoned in the kitchen is going to be toasted to a very successful chairing session at NAM, but also to all 300,000 of you that for some reason want to chat space with me. All right, it's day 4 here at NAM, and we are starting early this morning because at 9 a.m. it is the second of the low surface brightness galaxies session, following on from the session that I chaired yesterday. So some more talk all about that, which I'm excited for. Then after that at 11 is the poster session, which is always my favorite session when I go to conferences. So, you know, usually in the sessions that you have and the time you have, an hour and a half, right? There's not enough time for everybody who wants to talk. Usually just like 6 people get to present their work. So instead, people request posters to showcase what they've been doing as well. And usually that's undergrads and maybe like first year PhD students who've been doing research as well. Perhaps those who aren't, you know, as confident yet to give a talk. And this is why it's one of my favorite sessions when I go to conferences as well, because I just love like chatting to people, finding out all the research they've been doing, but also just, you know, giving them a little bit of a confidence boost that they might need as well, being like, yes, this is great work. Now, usually this would be in a big exhibition hall, right? But because it's virtual, it's not. And I was a bit worried about how they would actually go about doing this like if you couldn't do it like actually in person with people wandering around and chatting to each other, but they're actually doing it in Gather Town, which I think will really work. And I think it's going to give me that bit of the conference I've been missing so far, the sort of networking, meeting new people very organically, just bumping into someone or seeing a poster that you're interested in and just chatting to them and then wandering away. You can actually do that on Gather Town. So I'm really looking forward to that. I'm just going to wander around and speak to, any posters on galaxies or supermassive black holes that, take my interest, or any others that take my interest as I wander around as well. I'm also squeezing in a recording of the Supermassive podcast this morning as well, which is the podcast that I co-host for the Royal Astronomical Society. So because NAM is their conference, it made sense for us to record one at NAM. And the theme is actually all about the Van Allen radiation belts, which are really cool because there's been some new research presented about the Van Allen belts as well at NAM this week. That podcast should be out by the time this video comes out, so I'll link it in the video description below if you want to check it out and give it a listen. In fact, check out the whole back catalogue of Supermassive podcasts. After that, this afternoon, I'm very excited for a plenary that is going on this afternoon, which is being given by Professor Sandra Faber. She is an expert in galaxies and evolution and supermassive black holes and how it all ties together. So it's very relevant to my research as well. So I'm going to be taking lots of notes during that probably. And then this afternoon is the first two of the 3 blocks that we've got for a session that I've organized, which is called Beyond One Dimension. So this it's all about observing galaxies, not just with a single observation, but with many of them. So it's something called an integral field unit. And essentially you can think of that as either taking an image of a galaxy at every single wavelength or getting a spectrum of a galaxy at every single little pixel, a little point in the galaxy. And it essentially enables you to see galaxies in so much more detail than we've ever been able to before and pull all that out. So again, this is so relevant for my research because this is the kind of data I'm using at the minute as well. So I'm really excited to hear from people about what they're doing with that data, like what bits they're able to pull out from it, whether that's star formation rate or kinematics or something like that. I'm really excited. So I'm going to be concentrating quite hard in those sessions, probably taking a lot of notes. And that's why I've done this big spiel of a vlog this morning for you all, because I didn't want to get distracted throughout the rest of the day. But I will check in with you at the end of the day and let you know how everything went.
Much later.
All right, it's the end of day 4 here, and my poor computer sounds like it's about to take off. I think it's just really, really hot. Like, I am in this room as well. Honestly, it's sweltering. I'm absolutely melting. But such a good day of talks. Like, I have so many notes and, like, screenshots of slides and stuff like that. So, obviously a good day if you judge it by how many notes you've taken. I really enjoyed the plenary this afternoon by Professor Sandra Faber, especially because it made me figure out something that was wrong with a project that I was doing. I knew there was an error in there. I knew there was something wrong that needed fixing, but I couldn't quite figure out what it was, and it made me realize what that was. So I was obviously really grateful for that, and just sort of the big picture context stuff that she talks about with respect to my work as well. And now it's just time to chill because it's a big day tomorrow. It's the big day. It's the last day, but it's also the day that I'm talking about my research as well. So I think my talk is ready to go. Probably gonna practice it in the morning, but just try and chill for this evening now. In the sunshine, with a drink, obviously. All right, day 5, which is the big day. You'll notice I even did my hair this morning, which in the heat was excruciating, and I did my makeup as well, just so I can feel, a little bit more professional, get sort of like psyched up for talking to people this afternoon. I will get changed before I give my talk, but I'm going to stay in my scruffs for now. It should be a fairly chilled day compared to yesterday. The sessions this morning, none of them are really directly relevant for my research, so I'm going to skip them in favour of practicing my talk instead and, just checking that I'm all comfortable with it. I will be going to the plenary this afternoon though, which is by one of my colleagues, Nick Bonn, and his project at the University of Portsmouth called Tactile Universe. They 3D print these amazing models of galaxies to engage visually impaired people with astronomy as well. Astronomy being an imaging science, it's possibly a science that visually impaired community have been excluded from for a long time. And so they're thinking of new and different ways to engage that community. There's loads of free resources too, so I'm going to put the links down in the description below if you know of anybody that would appreciate those resources, and also the free 3D models so you can print them at home if you want to as well. After lunch, there's another block of sessions that, again, is not directly relevant to what I do, so I might, again, skip them in favour of practicing my talk. Maybe I'll just like dip in and out of them. But then come 4 o'clock is the session that I'm presenting in, and I've got the graveyard shift because I'm not speaking until 5 o'clock. It's the penultimate talk of the day, the penultimate talk of the conference at 5 o'clock. So I don't even know if that many people are still going to be around at that point, or have, you know, just sort of wilted away in this heat and ended up outside instead. Hopefully some of the Americans that are attending might still be there anyway, you know, because it's not even lunchtime for them yet. So keep your fingers crossed that my talk goes well, and I will see you after I've given my talk.
Much later.
Okay, we're done. We're done. The session is done. I think my talk went well. I mean, it's so hard to judge with these things, right? When you're literally just like talking into a void, you're not getting anything back from the audience when it's virtual. You can't even see the audience either. So it's so hard to judge. I got a few questions in the 3 minutes or so time that we had for questions, which is always good. You know, you want to engage people enough that they ask follow-up questions. So I guess that's one way of judging it. I think it went well. You know, maybe I'll get some emails at the beginning of next week who are like, oh, I saw your talk. Have you thought about this? Or have you read this paper? So I guess I'll know a little bit more next week. But I guess you want to know, like, what did I actually talk about? Like, what have I found in my research? Well, we're going to need a bit of background info first. So there's this really famous diagram in my field of research showing how the mass of a supermassive black hole in the center of a galaxy is correlated with the mass of stars that you find at the centers of galaxies. It's something we call a galaxy's central bulge. And the way these bulges are formed are in mergers of 2 galaxies. Essentially, the gravitational forces move stars from sort of nice, ordered orbits into like chaotic ones that I always say resemble a little bit like a beehive. And if you have like a major catastrophic merger like what the Milky Way and Andromeda are supposed to be going through in a couple of billion years, you can actually completely destroy the spiral shape entirely, and you get left with something that is essentially pure bulge, 100% beehive chaos. And so because the mass of this central bulge is correlated with the central black hole, people thought, okay, mergers must grow black holes and bulges and galaxies overall simultaneously. They must evolve together, something we call co-evolution. But a few years ago, me and my collaborators were like, well, what about galaxies that don't have mergers? Do they have tiny black holes? This would be one way of actually checking that hypothesis. Of course, first we had to find galaxies that hadn't had a merger. So those are the galaxies without these central bulges. If you think of a galaxy with a bulge as like 2 fried eggs, like back to back, and the bulge is the egg yolk, like we were looking for like egg white omelets, essentially. And from a huge big survey of the sky that had detected 1 million galaxies, we managed to pick out 100 galaxies, these egg white omelets that we were looking for, that happen to have growing black holes. And if they have growing black holes, you're able to measure the mass of the black hole. Because if a black hole is growing, essentially what it means is that it has matter spiraling around it that it will eventually accrete, which is a fancy physics word for eat, essentially. That matter is accelerated by the black hole, and then due to friction, the speeds it's moving at, it starts to glow very, very brightly so that we can see it in the universe. It tends to be that black holes are some of the brightest objects in the universe, weirdly, just because of the material spiraling around them. And it's this material that's spiraling around that lets you know so much about the black hole, right? So if you could work out the speed that it's spiraling around the black hole, you could actually know how big the thing is that it's spiraling around, right? You can actually get at the mass of the black hole. And you can get at the speed from how much the light is blue shifted and red shifted away from you as it spirals around. So we did that. And also from this light, from how much light it's giving off, you can tell how much material per year the black hole is accreting. Like in suns per year, how much is the black hole growing by? So we did both of those things for a paper back in 2017. And we found that these galaxies have black holes that are way more massive than you expect. As big as the supermassive black holes in galaxies that had had mergers. And we even had some simulation friends look into this too, and they found the same thing in their simulations. And they also could then look at how the mass in those black holes had got there, and found that only 35% of all the stuff, all the matter in black holes today, got there because of mergers. The rest, 65% of all the stuff in black holes, is something else, some non-merger process. So the question is, what is that non-merger process, or what are those non-merger processes that can do this? Because it has to be something that's internal to the galaxy, right? Because these galaxies have been left alone their entire lives, never merged with another galaxy. So it has to be something about the galaxy itself, right? It's like nature versus nurture. It's something about the galaxy that the galaxy can do on its own with no sort of external influence. And working out what process that is essentially my job and what my research has been on for the past couple of years, right? And the way that I do that is to say, okay, well, how much matter is being funneled towards the centers of these galaxies where you find the black hole? And then I can compare that to simulations of different processes that we know can funnel gas. For example, like the spiral arms in a galaxy we think can funnel gas down them. Also, the bar structures we see in galaxies can funnel gas down them. And from the numbers you find, you then try and narrow it down. Now you're probably thinking, well, how do you get at the rate that material's being funneled into the centers of galaxies, right? Well, you have to make a simplifying assumption here. Now, you know it has to be at least the rate that the black hole is growing. But the other thing that black holes do is also they tend to burp if they overeat. So this is material that's actually thrown out from the regions around the black hole, not the black hole itself, because nothing can escape a black hole because nothing can travel faster than the speed of light. But this region, this is what we call the accretion disk of the spiraling material. The pressures can increase and increase and increase, so much so that pressure has to be released into what we call an outflow into the galaxy. So that inflow rate to the center has to be at least the accretion rate plus whatever rate the galaxy is outflowing its material at. So we'd already measured the rate that these black holes were growing at. What we needed was this rate that they were outflowing material at, the rate that they were burping up material, right? And that's not an easy number to get at. What you need to do that is IFU data, the stuff that I was talking about before, where you get an image of the galaxy at every single wavelength, or you can think of it as like a spectrum at every single pixel. And then that lets you pick out the material that's been excited by this burp from the black hole. So we actually observed 4 of these bulbous galaxies, these egg white omelets. I'm showing them here. These are actually the Hubble Space Telescope images, so they're absolutely fabulous. Our data, unfortunately, does not look like this. We actually observed them with the Keck telescopes on Mauna Kea in Hawaii and got data like this. And I just want to say a massive thank you to the native population for allowing that kind of science to happen on what I know is such sacred ground to you. So I am very, very grateful for that. So this is the data we got from this IFU. I'm just showing you like what's called the spectrum for 1 pixel, where you split the light into its component wavelengths, and you can see where hydrogen has been ionized and also oxygen has been triply ionized. So this is when you cause the electrons in oxygen to jump up energy levels, which they're not supposed to be there, so they drop back down to give off a very specific wavelength of light. We can then pick out those very specific wavelengths of light in the spectrum and pick out which ones are coming from the outflow, which we know is coming towards us, which has been blue shifted. It's this little component here that I'm showing by the blue line, and we've essentially fitted to the data, and we've been able to pick out the stuff that's coming from the center that isn't blue shifted and the stuff that's coming from this outflow that is blue shifted. Once we did those fits and we could pick out, okay, what's the light that's actually coming from the outflow alone, you can then make an image that's just the light from the outflow. And from how bright this image is, you essentially work out, okay, how much material is there, and you combine it with how fast it's moving and how far it's gone to get at the rate that the material outflowed from the supermassive black hole. So essentially, this is the data that I've been working with for the past year or so, and the measurements that I've been making. I wrote that up into a paper that I've also submitted to a journal very recently as well, which is, hooray, a big achievement. And also have presented it at NAM just, to spread the word about what I've found. So the rates of inflow that I actually found into the centers of these black holes range from about 0.2 to about 0.7 times the mass of the sun in a year. And all these images I've been showing you are actually the slides that I showed in my presentation as well. And you can see that these different internal processes to a galaxy, bars, spiral arms, something we call cold accretion from the surrounding halo, they're all capable of driving inflows and simulations that well exceed those values that we found. And the really cool result was how energetic these outflows were. They're no different from, your typical outflow you would expect from a galaxy that's grown by a merger, which is weird because the galaxies that it's coming from is weird, and yet the outflows aren't weird. Also, these outflows have enough energy to actually escape the galaxy as well. They exceed the escape velocity of the galaxy. So that's really interesting. It could be that the black hole, with its big burp, is actually taking gas away from the galaxy that it could use to make more stars. Although we're going to try and confirm that in some future work that that's actually happening. So even without a merger, you can grow a supermassive black hole, and you can also provide enough material for an outflow that could even impact the entire galaxy. Right, sort of like the galaxy shooting itself in the foot a little bit. And this has just sort of turned everything we thought we knew about how black holes and galaxies grew and co-evolved together just completely on its head. So this is why I was so excited to, see what people's reactions would be and get their thoughts and feelings. So I'm hoping I'll have a couple of emails next week. The paper that I've submitted is currently in peer review. So one of my colleagues, who may have been in the talk as well, is currently reading it and commenting and providing feedback and deciding if it should be published in the journal or not, like if it's worthy of publication, if it's good science. I'll update you all over on Twitter and Instagram about how that process goes, like if the feedback from the referee was good or bad, and hopefully I can let you all know when it's finally accepted as well. That'll be a good day. But for now, that's NAM over and done with for another year, which is crazy. It feels like yesterday that I went to my first NAM back in 2014 when I was a little fresh-faced PhD student. Now it's like 7 NAMs later or something, and I'm just like, yeah, I'm a postdoc who knows my stuff, who gives talks. It's very exciting. It really, feels like you live in the dream. But hopefully next year we'll all be back in person for NAM, which I'm really hoping that'll be the case. And of course, if we are, I'll bring you along for the ride as well. A huge thank you to this week's video sponsor, Brilliant. Brilliant is a website and an app with interactive courses on a huge range of science and maths topics. Now, you've probably heard me talk about Brilliant before, but recently they've upped the interactivity level on their platform to just a whole other level. And I think that learning in this way, by doing and interacting, is one of the best ways to learn something new. And I always get comments and messages from people that say they want to be an astrophysicist or a scientist as well, but they're no good at maths, and so what should they do? And I always say, practice, practice, practice. Until it becomes second nature, just a language to use to describe the fun stuff like black holes. So how about taking it back to the foundations of maths and algebra, figuring out the proofs to equations like Pythagoras' theorem, for example, just interactively with the courses on Brilliant. So if that sounds like something that you'd be up for, head to brilliant.org/Dr. Becky, or you can click on the link in the video description down below, and you can sign up completely for free, joining a community of over 8 million people who are learning something new with Brilliant. That is exactly what we like to hear. So thank you again to Brilliant for supporting this channel. /Dr. Becky, or you can click in the link on, why do I say in the link? On the link. /Dr. Becky, or you can click on the link. I got so excited that I said on. Oh, huge masses. And the cars are really starting to annoy me, but I can't close the window because it's so hot in here.